Yeah, so I'm going to talk this morning mostly about the geospatial capabilities of AllegroGraph. We looked beforehand at the people that signed up for this seminar, and we saw that probably more than half come from the semantic web community, the people really familiar with RDF. And then there's a slightly smaller group that is from the geospatial community. And for them, shall explain a little bit more about our RDF triple store. So I thought before I go into my presentation, I talk just a little bit about why the RDF community needs geotemporal reasoning capabilities. If you now look at what RDF is doing on the web, you see that people are basically tagging most of the things that now happen in web pages also with say a little Google map or Yahoo map. So geotagging has become very, very common, and you also see it more and more in RDF projects. RDF projects are about people and their relationships and events that happen in space and time, so it's becoming more and more clear that reasoning about time and space really needs to be an integral part of the semantic web. Now, if you look at the geospatial community, you also see more and more interest in RDF because RDF is all about metadata. Sorry. And the tool that the geospatial people have right now is mostly about visualization or analytics, but not so much about storing metadata. One thing about metadata is that it's usually very unstructured and sparse, and you want to be able to keep adding more annotations and types of predicates all the time. So you need flexible technology for that. And then what you also see is that geospatial databases contain a lot of information that are not well described in relational databases because it's actually about objects and object hierarchies and about relationships between objects. So, for example, one thing that you see is that people start to use ontologies to describe geospatial objects. Just one really nice example is the National Map Project that uses ontologies to make it easier to take all the layers of information that they have in the databases and do queries that go through all the layers. So if you want to know more about this project, you have to go to nationalmap.gov. I will also be part of this discussion. Actually, there's a meeting next week about this. So I will be in the Washington area. And if there's people that want to talk about my presentation today, you can meet me in Washington early next week. So now let's go into the presentation. I will talk, for those people that are not so familiar with triple stores, a little bit about what you do with a triple store. I will show how you also can store events in a triple store, where events are defined as a combination of something that has a begin time and an end time, a location, probably some actors, and a type. I show how we can use one query language to combine reasoning over events. So we have this query language that combines geospatial, temporal, social network analysis. And then I will talk mostly about geo after that. I will give a small geospatial tutorial that I've given before in one of the seminars. But then I will talk about two new things that we're working here at France. One is we show how you can, for example, play with a river network, a big graph, where we take some river network data from British Columbia. We do some graph search and spatial operations on that database. We output data in KML, and we can show it in Google Earth. So that's the first example. And then the second thing is a research direction. We have several customers that have talked to us about moving objects, tracking, say, tracking animals or soldiers or trucks or airplanes or even telecom mobile phone users, and if we can do something with that. So I'll talk about what we've done so far on this topic of moving objects. But okay, let's go into the basics of a triple store first. So for people that are mostly familiar with relational databases, a triple store is quite different. With a relational database, you begin with thinking hard about your data. Then you create schemas, and then once you've got your schemas and you put them into your database, then you can start adding data and refining your schemas. With the triple store, you basically just open the triple store. This is I will show the first examples in how we do it in Python. So I create a triple store, seminar.db, and I'm ready. Then I can add some regular data. I can say that person 1 has a first name Steve, who is an organizer, and he's 52. I can tell something about myself. I say first name Jans is a psychologist and 50. And another person who's Craig, a salesperson, and 32. So what you see is I haven't added any schema data. I just entered data. I can say whatever I want. One distinguishing characteristic of a triple store is that one-to-many relationships are directly encoded. So I can say person 1 is a colleague of person 2 and person 1 is a colleague of person 3. And because I just want to say something, I say person 1 likes pizza. So now we have a bunch of triples, and actually these triples all together form a graph. So here you see our graph, which is our AllegroGraph browser. And what you see in here is the nodes that I created are the vertices, and then the edges are the links between the nodes. And on the left-hand side, you can see what the arrows mean. So, and you can just keep on adding data. Say another one-to-many relationship. Person 3 is a neighbor of person 1 and person 2. And now we see that there's some more relationships between person 1 and person 3. We have a query language. Well, we use the query language SPARQL. This is our internal language, but we can do the same thing as SPARQL, where we say select every X name and Y name, where X is a colleague of Y and not Y a neighbor of X, and X is a first name X name and Y is a first name Y name. So this is the typical kind of query you do with this type of database. Now, one other characteristic of triple stores is that they do reasoning, and this is the smallest reasoning tutorial on Earth. Basically, I say here that with this triple here, I say that every subject that has a predicate first name must be of type person. And if I add this triple to the database, then suddenly I see that person 3 and person 2 and person 1 are all of type person. Just by having this one little triple, I now suddenly have more information in my database. And then, because I want to lead on to the geospatial part, I can also put information about events. Say in my triple store, I can say there's an event 100 that is of RDF type meeting. I simplified the triples, by the way, for the RDF people that will say, hey, where are all the namespaces? You'll see the namespaces later, but I kept it simple for now. So I say event 100 is of type meeting. There's an actor person 3 and there's an actor person 2. And this event started at, well, at this particular time, and it ended at this particular time, and the location was in Berkeley. So we use latitudes and longitudes as pairs. We don't have separate triples for the longitude latitude. You can do that, of course, but we have an indexing scheme where we use them in pairs, a two-dimensional indexing scheme. And now you see here graph again, and you see that there's an event 100 that's related to person 2, person 3. It was a type meeting. This is the location, and this is the start and the end time. Yeah. So then, one of the things that we do, and one of the things why we get a lot of attention from people in the government, but also from marketeers, is we can do queries where we combine both temporal reasoning, spatial reasoning, and social network analysis. So we can take a query like, find a meeting that happened in July within 5 miles of Berkeley. It was attended by the most important person, Janss's friend, and friends of friends. If you look at this query, you see that the first 2 classes are social network analysis classes. So I say, find the ego group around the person Jans, 2 levels deep, put it all in group. And then for every X in this group, and start with the most important member in this group, find all the events that this particular actor X was in, where this event was of the RDF type meeting, and where the event happened in this time interval and in this particular geospatial bounding box. Okay, so this is the thing that people really like about this combination. But in the rest of my talk, I will only talk about geospatial reasoning. Okay?
There's one question I'm going to just ask before we go on. It's can a triple relationship have start and finish times without creating new triples to encode that data?
Can you say that again?
Can a triple have a start and finish time without creating new triples to encode that data? So encoding the interval information.
Well, one thing you can do is, actually I talk about triples, but for the RDF people among you, actually you are a quad store. So you can put, say, the start time in the object of a triple, and you can put the end time in the forward argument of the triple, or the graph argument of the triple. And then you would need only one triple to encode time. But actually, we've moved on beyond that, and we are working on 2D indexing for intervals too, where we put both the begin time and duration in one part in the object of a triple, and use 2D indexing on that. But that will be in a seminar on temporal reasoning with AllegroGraph. So geospatial. Well, we started out AllegroGraph as a RDF triple store / graph database, but we quickly found out that people really want to have geospatial information in there. So when we started working on that, we wanted the following things to be really efficient. The first one is, well, where did something happen? How far was this event from that event? Or, and this is actually at the heart of all spatial databases, find all the events that occurred in the bounding box or radius of n miles. So we've created a 2D indexing structure that's actually more efficient than an R tree for the geospatial people, to find all objects that happen within a particular radius. And then we deal with polygons, and we wanted to deal with the intersections of polygons. And of course, it has to happen on a really large scale when things don't fit in memory, and when you have millions of events and polygons. So that was the challenge that we, and we've now, I think, met most of these challenges in our geospatial database. So we work on both a flat plane and on a sphere, but you have to tell the database what you want to do. And we can work on different scales from angstrom to miles. And you can help the database by telling on what scale you want to work, because our indexing structure works better if you roughly tell the database whether you're working on the level of cities or countries, the world, or if you are designing chips and you want to work on a really small scale. If you want to work spherical, then we make sure that we do all the right mathematics. So when we do distances, you get the real Haversine distances between objects. And again, I wanted to stress that we get really fast times because we adapted a kind of an R-tree algorithm onto our indexing structure for our triple store. And here's the Wikipedia entry for those people that are interested in R-trees. And then the predicates that we support, actually this is kind of high-level support. We also have a lot of low-level predicates for this. But for example, one would be find the bounding box, or find every x that is in the bounding box between min-lat and max-lat and min-lon or max-lon, or find all the y that is within miles distance of a particular x. And I'll show that in a little while in my tutorial. For the RDF people, we do most of our geospatial work. We did most of our work so far in Prolog, but we now also support SPARQL. So we use the official SPARQL extension language, and you can do well, all the queries that you want just within SPARQL, the standard. Sometimes people want us to give a little bit more information about how efficient our database is, and for benchmarking we use the database called GeoNames. You can find it on the website geonames.org. There's a database with roughly, I think now almost 7 million places on Earth. It can be populated areas, but also can be like mountaintops or beaches or even post offices. And all in all, that gets you more than 110 million triples right now. And then if we say want to find all the 502 entries within 3 miles of the France offices, we can find it in 95 milliseconds. So that's relatively fast. Okay, so now before I go into the examples, the new work that we do at France with Geospatial, I first will switch to Lisp to give you a little example of how we work with the triple store and how we do our basic geospatial work. I do this demonstration in Lisp, although everything I show you is available in Java, and real soon also will be available in Python. I have to find this. So just for fun, let me create a triple store. So what I'm going to do is I'll show you a little bit about how to work with triples, just a little bit, and then I'll dive into the geospatial part. But just to show you how easy it is to work with a triple store, you create a triple store. So now I have a triple store. Sorry, on the right-hand side you have the editor with the script of expressions that I'm going to evaluate. On the left-hand side is a listener where you will see how things get executed. So this is the place where I could type 1, I get 1 back. I can type plus 1 and 1, I get 2 back. So this is the listener. Okay, so I'm working with IDF, but I'm lazy and I don't want to type these long namespaces. So basically what I say is that I register a namespace, in this case O, to stand for this longer namespace. So I register it. And now I can just say add triple, person 1 is the first name, Steve organized in 52, the basic thing I did in the PowerPoint. Jans is a psychologist in 15, Frank is a salesperson 33. And then some more triples. And here I have graph, which is this graphical user interface. I can take this person and I can also look at it this way. So now it's more like a database view where I can, this is person 1 who's got an age, colleague of, first name, likes and type. I can click here and then I jump to person 3. And I can even do SPARQL expressions, type them here and then I get here the results. This is a graphical user interface. And that's about it, what I'm going to show you how the triple store works. Let's go to the geospatial example. So I will close all the triple stores and I will open a subsection of the GeoNames database that basically contains all the populated areas in the US. And I register another namespace. I tell the database that I want to work on a level of 5 miles. And then let's do some queries. Well, first let me show you what the data consists of. So here is the context of the database. So for example, there's a city with the ID 5374671, which has the administration code CA for California. Actually, I can click on California and then I get to see all the places that we have in California. And let me go back. It's got the ASCII name Moraga. It's my hometown. It's in the country US. Let's not click on that one to give it a whole bunch. The elevation is 152 meters. It's a populated area. And here's the location, which is done as a pair, so 37 and minus 122. Anyway, so this is roughly the data that you have in this database. And I can click on anyone here. And so this is a little place called Avocado Hates. Anyway, you get the point. So let's now do some queries. So for example, I say here, find every X where in the database X has the ASCII name Berkeley. And then find on the left-hand side that there's actually 3 places in the United States. So now let's take this query here and say, find every person X that has the ASCII name Berkeley where the administration code is California, and then print this particular person. And so now, oops, I've done this in N triples format. So now we find that this particular place has the name Berkeley. It's a populated area. This is the longitude, latitude, the population, etc., etc. Now this has got nothing to do with geospatial. This is just RDF search. So let's look for my hometown and where it is. So I say select the position where X has the ASCII name Moraga and X is at position POS. So I select that and I get here longitude, latitude. So then I can look at Berkeley, which is close to my house. So I say find the X that is Berkeley in California and find the position 2. And now I find that it's actually very close to my house. So now let's find how close we are together. So give me the distance back where X is the name Moraga and Y is the name Berkeley and Y and this Y is in California, and the distance between X and Y is distance. And I get this back and I find that the distance is 8.2 miles. Yeah. So this is the first little bit of geospatial. Of course I can find, now let's go to the next one. The next query is, okay, give me the name of an X that has the name Moraga, where Y is within 10 miles of X. And I execute this query, and I get a list here of cities that are around Moraga, and I can say how long is this, the length of the last expression. So there's 18 cities around my hometown within 10 miles. And let's just show it. So I say put in the Google map everything, a list of things with the name, a latitude and a longitude, where X is the name Moraga, and X and Y is within 10 miles of Moraga, and Y is the name, and Y is at a particular position, and then I unravel the position into a longitude and a latitude, and I show a hybrid map in Google. And then Google's a little bit slow today. Okay, and then I find all the places around my hometown, Moraga. Now we also do polygons, so please don't look at this code, it's just a little bit code. But say I make a region from the cities Pinole, Berkeley, Emeryville, Denville, and Concord. So I create this region, and I show in the region what the particular polygon is. So now you, oops, I should put my mouse here, sorry. So you see the polygon here, and now I want to know, give me all the places inside. So I say, given my region, find all the places that are within this region and give me back the longitude and the latitude where the particular place that I find at this particular name. And now I see the cities within this polygon. Okay, so that is just the simple way to take geospatial data and do queries over them. Again, I want to stress that if you want to do this in Java, because most of the people on the line probably will be using Java or Python, you can do this both in Python and within a few weeks also in Python. If you want to see how you do this in Java, then go to our website, and then you go to AllegroGraph, and you go to the Learning Center, and then you will find, I hope everyone can keep up with the speed with which I'm doing this, but here you find how you can work with geospatial primitives in our database. You can click on this, and each of these things will all work. Actually, this whole Learning Center, if you run Java in Eclipse, you can take all these examples in one big Eclipse project, and you can run each of these examples straight out of the box with our free Java edition of the product. Okay, let's go back to the presentation. So we talked about this. So now We're doing several projects with Geospatial here at France, and I just wanted to talk about two of these projects. The first one is where we work with one of the layers of the geospatial database of GeoBC, a government organization in British Columbia. So we take a river network, and of course most people will realize that a river network is a graph. So for example, if you take here a drainage area, you will see here a little river with the drainage area on the left-hand side and right-hand side. Basically how you represent it is you take, if you represent this as a graph, you take from here to here, and then this is your first segment, and then you have two upstreams here, and each little segment has a left drainage area and a right drainage area. And these things can be really pretty big. The one we're working with has 6 million line segments for all the rivers in and all the drainage networks in British Columbia. Now how we represent it is fairly simple. We say there's a segment of type stream segment. The segment will have multiple upstreams and a left drainage area and a right drainage area, and we actually only represent the downstream position of a particular segment. And then the type of queries that we do, which you can't do with any spatial database so far, is where we actually combine the graph search on a graph database, and I'll go into detail a little bit more later, and the geospatial capability. So for example, given a polluted segment S1, find all the upstream segments within 50 miles of city 1200. Yeah. Or given the polluted drainage area D1, find all the schools in the rectangle X1, well, whatever, that might be influenced. So what we do with our queries is we do plain graph search, where you find all the upstreams or downstreams of a segment, or we do graph search with bounding boxes. And this is just the query that I just talked about. So we actually implemented this upstream search in and downstream search in Prolog. So here, and don't even try to understand it right now in this seminar, but you can do this later when we publish this this PowerPoint file. But here you see the three definitions that will define how you look upwards in a river network, and then when you execute it, you get something that most people will find. So here we take, say, one segment and we say, okay, find all the upstream edges. And then we execute it. You get a really long list of edges. Some people might find this unreadable. They really prefer something readable like XML. Yeah. So here you see XML, which is the rendering language for Google Maps and Google Earth. Here you see some setups, so you see some titles and how you want to do the coloring, and then here's the actual data of line strings that have an ID. You say that it's tessellated, meaning that it should follow the Earth surface, and then you just get the coordinates, the XY, XY, per each line string in your database. And then how does that look like? Well, let me show you. If I can find my desktop somewhere, I go to Google Earth. Actually, I want to disable this. So what we did is we have a server here at France with this river network, and we can do, say, a query where we say, okay, show me all the upstreams for this particular node 710281.837, and then I can look at it and I can fly there. Now this is done for a webinar, so I guess everyone in the geo communities is intimately familiar with Google Earth, but you will also understand that it doesn't really work that nice on a webinar, but I still wanted to try for the people with fast connections. So now we are looking for this little point here on the right. So I'll wait a few seconds for those who can't see it. So we've taken this point here, And then we find all the upstreams. Of course, I can fly in there, so I can find another one of the points roughly around here, and I will fly there. Again, it won't look that pretty for people with slower connections. And so here you see a drainage area somewhere in the mountains that is described by this data. And I will just show you how you can actually turn around. Oh, let me see to that. It's in the middle of, sorry. So here you have a better view of a part of the river network. Now, one of the things that we also did is a little demo of how you can take, say, a particular bounding box, look at all the rivers that stream through it, and then find all the upstreams that go through this particular box. So let me try to see if I can fly there. Let me take this. Now we should have taken probably a slightly better color, but look here. Here you see, well, let me wait a few seconds so that everyone can see it. So here you see a part of the same river network. Now say if you take this box here, the little red box, I hope you can see it on the webinar, then if I disable it, it gets slightly more blue. So the query that we do is we say, okay, given this particular box, give me all the upstreams that go through this box. So I can click, and now you see it suddenly gets slightly whiter. I hope you see that on webinar. Anyway, so this is how we play with Google Earth and with these data sets. And we do our combined graph search and geospatial search. Let me go back here. If you want to know about KML, there's a wonderful KML tutorial on the Google website. If you want to know how we created this data, I'll leave this code in the PowerPoint presentation. Don't even try to look at it right now. But the point is, you could write the same stuff in Python or 5 times as long in Java. But you can write the same code and generate these same maps from the geospatial databases. We are thinking of doing something more general for KML. We're thinking of providing some templates, so it's fairly easy to get the top of your XML file right, and then we will provide some general tools to make it easy to display a whole bunch of points or line segments or polygons. But again, please let us know what you want, because you might have completely different wishes for how to generate KML from a triple store. Okay, so that was the first project we do. The other thing is that we have a customer that is actually interested not only in static objects and doing analysis on them, but on objects that actually move. And I'm sorry, I can't talk about what this particular customer is doing, but we've in the past talked to various people that work with fleets of trucks or swarms of airplanes, people that have track data for soldiers or track data for endangered animals, where people are actually tracking a salmon swimming up a river or swimming in the sea, the ocean. And then there is all these new telecommunication services where you have people walking around with their cell phone, where the cell phone is a wonderful GeoTemporal sensor. And what you want to do is services where you, if 2 friends or 3 friends that satisfy some criteria and they're close together, that you send them a warning. So it's a new topic that I see coming. And well, we have this one customer that wants us to look deeper into this. So we're doing our first projects in this area. We're actually very much inspired by this book called Moving Object Databases by Güting and Schneider. The challenge that we have is that we need to track more than 1 million objects, and at a resolution of, well, at least once per minute their location. But if they change more than so many meters, we also have to track that. And we have to deal with that both in real time and historically. So if you track people real time, you just can't put it in a database and have rules, look at 1 million people. Just relational databases and also a triple store won't just be fast enough to deal with that. So what you want is to use techniques from the gaming industry where you have all these objects in memory and do some clever indexing there. And then you need some rule sets that allow you to trigger on particular configurations of objects in space and time. But in addition to that, you also want to take your real-time data and do some aggregation and some data filtering, and then store the right amount of data in your database, and then do analysis on that data. So and by the way, for this we are very inspired by the book by Hanan Samet, one of the granddaddies of this the field of multidimensional indexing. The type of questions you need to answer is, okay, so we have 5 soldiers that have been active less than 8 hours with training X and equipment Y within a mile distance of each other, or find, and this is say for a FedEx, find another truck that can pick up package X at location Y so that I can pick up package A at location B so we both will arrive at P before time T. So that's the typical hard questions you do when you deal with moving objects. So far we have implemented a number of things. We have an internal object model for representing active objects, and then do a real-time 3D indexing using a grid approach that gamers also use. We've implemented simple rules to trigger actions based on in-memory objects. And then another thing, which is harder than you might think, is that if you have moving objects, you really don't want to store everything they do. You only want to do enough so that you can do your historical analysis later. So we've also been working on, okay, what is it what you actually store on hard disk or in your triple store for later historic analysis. And then what we've implemented for historic data, so for the static data, is new 3-dimensional indices. And we found that in many cases you actually have to index your data twice, once for X, Y, T, and once for time, and then X and Y. And then the kind of functors that we right now are building is, for example, find every A in a particular bounding box within a particular duration. And you can specify this both with all the parameters, although it's a lot easier to read if you have a box, a geo box object and a time box object. You want to know if you have a particular person A and B within a particular time box in what the distance was. If you specify only the A, you get a lot of data, but it's doable. If you have only the B, it's doable. If you leave out both, then you basically explode your queries. And then you want to look at whether 2 animals, for example, crossed at a particular place at the same at a particular time. And so we provide functors for that too. But again, this is research at France, and we're still working on it, and we're actually hoping for people to ask us questions about this and to challenge us some more. So suggestions will be very welcome. And this also concludes my talk. Thank you very much.
Okay, yeah, thank you very much. I'm going to open it up for questions. There's a follow-on to the first question that provides an example to try to get more at what the question was. I'll repeat the first question. It's about the relationship. A triple will have a start and finish times without creating new triples. And here's an example. An employee relationship that is not forever.
Yeah, that's an interesting one. So the point is, if you say have an employee relationship that has a begin time and an end time, then you probably also want to represent it as an event, and you're probably going to need multiple triples actually to represent it as an event. For example, we did a little work on the royal family in the Great Britain through the ages, and then of course people also are married to multiple people, sometimes even up to 8, and so each marriage is basically an event between 2 actors. So you need multiple actors for that, multiple events. Actually, there were even overlapping events. Have you done, okay, one question is, have you done any work with grid coordinate systems like MGRS? No, we haven't done so. I have studied it. It makes life, when dealing with data, in most cases a lot simpler because you can treat parts of the world just as flat spaces and then your computations become faster. We haven't really looked into that, although AllegroGraph does allow you to work in simple 2D, not spherical. So then you just have an XY coordinate system, which again is also easier to deal with.
Okay, here's one. How does the database scale in terms of concurrent queries?
Right now we serialize queries. So we have done experiments with when you do short queries where we can do hundreds of queries per second. If there are long ones there, then everyone else has to wait. So the next release of AllegroGraph is actually mostly focused completely on the concurrency issue, where we hope to have hundreds of, maybe thousands of concurrent users where no one will have to wait for that one really long query. This is a really hard question from, I think, John Pastor. John, I have to think about that. I'll talk to you later. Okay, any other questions?
When will that new version come out?
I guess it's the person that is talking about the concurrency. So the high concurrency version will be out in beta halfway May, and we will announce it as a commercial product at the Semantic in San Jose in June. So then the question is, sorry, this is a really small window. Can we make this bigger? Okay, so one of the questions is, we, the Food and Agriculture Organization of the United Nations, have a geopolitical ontology written in OWL. Can you apply your tool to this geopolitical ontology? Is it only country level, so it's simple? Yes, so we in AllegroGraph support what we call OWL Lite or RDF++. So if you don't use complex restrictions, then we can deal with everything in RDF and most of the OWL predicates. Okay, I think that were most of the questions.
Okay. Well, we got everything done on time today. I'll be processing this video, and when it's posted on our website,